In the syllabus, you will be required to know how to determine the value of free fall acceleration g by experiment. It involves you using one of the kinematics equation s equals to ut plus half at squared applied to a falling object that moves through a distance s in a time of t. If the object was released from rest, then the initial velocity u will be equals to 0. And then if the only force acting is just the weight, the acceleration a is equals to g. So we would get s equals to half gt squared. If we are able to measure the distance fallen s and the time taken t, we would be able to find the value of g. However, there are limitations to this approach, namely in the way how time is measured. The time taken t to fall is usually very small, lasting only a few seconds. If a stopwatch is used for the timing, the uncertainty would be relatively large due to the human reaction time, which is between 0.1 to 0.5 seconds. Looking at the percentage uncertainty equation for time, we can see that a large absolute uncertainty over a small measured value would cause the percentage uncertainty of time to be large. A large percentage uncertainty in time in turn causes g to not be accurate. In order to get a higher accuracy for the value of g, there are modifications that we can do to the experiment. Firstly, we can set up the experiment in a dark room, and then we mount a meter rule vertically either behind or right next to the falling object. We then use a digital camera connected to a stroboscope to capture images of the falling object. A stroboscope is a light that flashes at regular time intervals according to a set frequency. If the frequency of the stroboscope is 50 Hz, it means that it flashes 50 times per second. The time interval between the flashes would be the reciprocal of the frequency, giving us 0.02 seconds. As the stroboscope flashes at regular intervals, the camera will take an image of the ball's position each time, so we will know the displacement of the falling object at different times. These images are superimposed onto a single image from which measurements of t² and s can be taken. In order to find the value of g, a graph of s against t² would be plotted. To better understand why we would plot a graph of s against t², it's important to look at the original kinematics equation that was applied to the falling object. Since the object was dropped from rest, the initial velocity u would be equals to 0, and since the only force acting was just the weight, the acceleration would be equals to g. So we end up with the final equation s is equals to half gt squared. We then compare that equation with the equation of a straight line, from which we will be able to see that the y-axis is s, and the x-axis would be t². The gradient would be equals to half g. There is no y-intercept here. If we were to plot a graph of s against t², we would get a straight line graph that passes through the origin, like what we are seeing over here. The gradient is equals to half g, from which the g can be calculated directly. Another variation of the graph can be plotted based on the original equation, where we square root it, giving us square root s equals to square root g over 2 times t. The y-axis is square root s, the x-axis is t, and the gradient is square root g over 2. Further improvements that can be made to the experiment include using an electromagnet to ensure that the ball is released from rest, and instead of a camera with stroboscope, we could use a video camera with timer, so that the ball's position at different times can be viewed frame by frame. When finding the value of a constant like g, it is often better to find a few different set of values and then plotting a graph so that the constant can be found from the gradient, as opposed to just finding a single set of value and then substituting them into an equation to find the constant. This is because of the two types of errors that we've learned in an earlier chapter. Firstly, when plotting a graph, random error is reduced. Random error is indicated by a scatter of points. By plotting a line of best fit, it has the same effect as taking the average of repeated readings, thereby reducing random errors. Secondly, it is unaffected by systematic error. Earlier, we've seen that the equation suggests that a straight line passes through the origin. If we have a plotted line that appears to be shifted on either side of the true line, this is indication of systematic error. However, the value of the constant, which is given by the gradient, would be unaffected, assuming that the gradient remains the same.